Okay, we're going to begin with sampling distributions and central limit theorem. We're going to have this packet momentarily if you don't have it already. We're going to begin with vocabulary word of parameter. So that deals when we're talking about a population. So that is a population numerical measure. Okay, some kind of number that's given to us. It's a letter without a hat, so it's kind of like either plain U, or plain P, proportion, or plain sigma. So it deals with a whole population that we usually do not know, which is why we do sampling distributions to begin with. We take samples to find out about the population. And those samples that we do are called statistics. So statistics are numerical calculations, regarding our sample. So whenever we talk about a statistic, that's an actual calculation from our sample. Our sampling distribution means many small samples, and we're trying to gauge what the parameter is. That's the relation, the numerical measure of the entire population that we're trying to gauge. So when we do this sampling, we can run into four scenarios, kind of like a matrix. That matrix could yield the following four scenarios that deal with bias and variability. Now here we have a lot of bias, high bias, but low variability because our data are all collected together, very close together, our samples. Here we have considerable variability. Our dots are not close together at all, but we have pretty low bias because we're centered around the target. Over here, in our third scenario, we have high bias being far away from our target, but we also have variability, spread. Okay. In our fourth scenario, we have low bias and low variability, which is what we kind of hope for. So we're around the target and our data is close together. Those are the four basic shapes, four basic scenarios that we encounter with bias and variability. Okay, to try to take a nice simple approach to sampling distributions, we'll take a population that just has the numbers 1, 5, and 9 together, and we're going to take two at a time, two choices, and if we read carefully it says with replacement, which means we can't have the same choice twice. So we're going to take all samples of 2 out of a total population of 3. I know this is unrealistic, but it's good for beginning out to understand the principle. So what we do is we go in order. 1, 1, we could have 1, 5, or we could have 1, 9. Let me continue this forward. Let's start with the beginning of 5. You could have 5, 1, 5, 5, or 5, 9. Then we could start with 9. We could have 9, 1, 9, 5, and 9, 9. So in the bottom example, we have a population of 4 data elements, and again we're taking 2 at a time. Another way they could say this is it's taken from a large population, which means we assume kind of replacement. So in this particular case, we'll take 2 at a time at 4, so it could be 4, 4, 4, 5, 4, 7, and 4, 8, respectively. And we start with 5. It's good to go in order so you don't miss anything. 5, 4, 5, 5, 5, 7, 5, 8. Then we have 7, 4, 7, 5, 7, 7, and 7, 8. And in the last column, we start with 8. We have 8, 4, 8, 5, 8, 7, and 8, 8. So now we have all possible samples of size 2 from a population of 8. Okay, we're going to start here with an example where our sample contains 0, 4, 8, and 12. And we're going to list all the sample of size 2 of a population of these 4 numbers. So when we do that, it says from a large population. So when that happens, we're going to assume that we have replacement because the population is so large, when we take 1 out, it's not really going to affect our data that much. So hardly noticeable. So we list all our options for 2 sample size. We have 0, 0, 0, 4, 0, 8, 0, 12, 4, 0, 4, 4, 4, 8, 4, 12, and you begin with 8. You have 8, 0, 8, 4, 8, 8, 812, and then 12.0, 12.4, 12.8, and 12.12. So we take the X bar, the average of all our sample sizes, or samples of size 2. We get an average of 0 here, 2 here, 4 here, 6 here, 2, 4, 6, 8, 4, 6, 8, 10, 6, 8, 10, and 12. So we just took the averages of each of our samples of size 2 and listed them all out here. Now, in order to be able to find out what mu and sigma are, we go to our calculator. If you're not sure, you can figure out that the sample's average is going to be 6, but let's figure it out. So we go to our calculator, we enter information, I entered into L4 and L5. I did stat, okay, calc, 1 bar stats, do that again, stat, calc, 1 bar stats. Make sure you enter the right lists, your frequencies, and your data, and you'll see that you'll get X bar is equal to 6, and our standard deviation is 4.47, so that's where this comes from. You can imagine we have to take into account the sample size being 2 and what that does. So we have X bar, which was equal to 6 from above, and our standard deviation was 4.472. We have to take into account our sample size, so we have to divide out, 4.472 divided out by the square root of n, which in this case is 2. When we get that, we're going to get a new standard deviation, 3.162. So that standard deviation takes into account our sample size of 2. So in a very important limit theorem in the statistics of the central limit theorem, which basically says that no matter whether or not the distribution is normal or not, if we have a random sample of size n from a population that's not even normal, with a mean of mu and a standard deviation of sigma, population that we don't know, that's the parameter, that if the sample is large enough, usually that means above 30, and it's greater than or equal to 30, that's the general rule, okay, that it's approximated to a normal distribution with a mu of average mean value of mu and standard deviation of sigma over the square root of n. So that means we can assume we have a normal distribution if we have a sample size of 30 or greater, even if the distribution is not normal to begin with. But we have to remember to divide our standard deviation by the square root of the sample size. So to summarize the process, the central limit theorem says that you can start with any population with a mean of mu and a standard deviation of sigma. And let's take an example of a pizza shop, which sells pizza for $1.75 a slice and soda for 75 cents. People come in to buy different amounts of these. So we want to know, if I get, some people buy a slice, others buy a lot, we want to know what the typical purchase is. We have no idea about the distribution of prices, okay, about how much the average sale is. So what do? We decide on a sample size, okay, we call that n, we know that. We want to take lots and lots of small samples, okay, and then take the average of those samples. That's the idea. So we want to take like 500 of these small samples of size 10. So what the central theorem tells us, as we said a moment ago, is that the mean of the population is going to be the same as the mean of our samples. So if we take X bar, okay, for a sample, and we take many samples, for many samples, what it tells us is that our average of our averages are going to be really close to the population average of mu. That's what it tells us, and we can assume a normal approximation, a normal distribution. So finishing this example from the pizza store, we want to try to find out what the average sale price is of a total order in this pizza restaurant. So you take a look at this, take a look here, and we take a sample here, which represents a sample only. You can see that 33 people had an order about 250, but doesn't really tell us much. We don't have that many samples here. But as our samples increase, this is 500 samples right here. As we take a look at those, this is a larger sample. It starts to appear to be bell-shaped, but that's of sample size 3. So this is 500 samples of size 3. So we need our samples to be a little bit larger than that. So we take 500 samples of size 10. You could see that approximately the distribution is going to become bell-shaped and approximately normal. And that's what the central limit theorem tells us. If we take enough samples of a certain sample size, even though the population is not normal to begin with, we get approximated with a normal distribution. And we find out that the average, if we take the average of all our averages, then we get close to the average for the parameter for the population, which is about $4.01. So we figured out that the average sale is about $4.01 simply from taking samples of size 10, but lots and lots of those samples. So you could do this if you work for a company and you wanted to figure out what the average sale is. That's what you could do without only using a small amount of data from the whole population. Now, I said before that we want to get a sample size that's like 25 or 30 or higher. So if we increase that sample size to 25, okay, so here we have, this was 3, this was 10, 500 samples of 3, 500 samples of 10, now we have 500 samples of 25. You can see it's really starting to resemble a normal distribution right there. Sorry. With sample size 25, it's really getting close. And we still get right around $4.01, which is pretty close. So when we start class next time, we're going to do examples 6 and 7 together in class. I'm kind of flipping this around so we don't spend time with the direct instruction. We can kind of get right to it and do examples 6 and 7 next time. But feel free to get started ahead of time because you know what's coming. And there'll also be some flashcards on Quizlet available. And there'll be more to come. So and please pay attention to the questions in the video so you're really ready for class. All right? And respond to those. See you soon. Bye. I forgot to mention that we're also going to do some of these smaller samples on our own, just like we did in the previous section of the video. So we're gonna do a couple of these as well on our own or with a partner to make it'll go quite quickly. Since you watch the video and you answer the questions, you'll know what to do right away when you get started.